Hi there, I'm Alberto Gutierrez, and this is the Practical Actuary channel where we discuss all things related to actuarial data science. In today's video, we're diving into the practical side of Combined Actuarial Neural Nets, CANNs for short. And if you haven't watched my first video, where I reviewed the paper Yes We Can and discussed the various aspects of CANNs, make sure to check it out. The link is in the description below. In this tutorial, I will be walking you through the step-by-step process of building a CANN model in Python. So grab your coding gear and let's get started. Okay, so in this tutorial, we are going to build a number of models. These models will include the generalized linear models, so basic, simple GLM. Will be fitting an elastic net. An elastic net is the penalized GLM with the lasso and ridge penalties. We'll be fitting a generalized additive model, or GAN. We'll also be fitting a basic feed-forward neural network. And finally, we'll be fitting a combined actuarial neural network, or CANN. So this notebook that I have will contain basically data analyzing, analyzing the data, some pre-processing before modeling, some modeling training, and then there will be some performance evaluation of the models. So yeah, let's get started. The data that I'll be using is the French insurance dataset. It's well known, so it's the French MTPL2 frequency. This dataset can be found on the internet. I found mine on Kaggle. I just downloaded it in my local machine and just read it into a pandas data frame, as you can see here. So yeah, this is just a high-level info of the data frame itself. But there's a better way of doing a quick exploratory data analysis. And my favorite package is SweetViz. So SweetViz is a brilliant package to do very quick exploratory data analysis. In just 2 lines of code, it basically develops a report which we'll go through right now. So this is the SweetViz report. So it does tell you the number of rows, there's any duplicates, the amount of RAM it takes, the number of columns, which of them are categorical, which of them are numerical, which of them are text. And yeah, so we start off with an association table that basically gives the correlation between the various variables. So one example is the area and density. So this is the population density with an area. This is highly correlated, as we expect. And then the other, for example, negative correlation is between driver age and the bonus malus. That has a negative correlation. So I think it's a very good association table, just to get a feel in terms of what variables are correlated with each other, so that one can better interpret the model results. Cool. So that's the association. The report also allows you to go over each variables and looks at the stats in terms of the number of distinct, the min, max, the range, the average, the median, the distribution in terms of the most frequent values, the smallest values and the largest values. Yeah, so we'll dive into number of claims. So the number of claims does range between 0 and 16. And the distribution can also be obtained here. Not really useful to see through the graph, but we can see here through the table. So about 95% of our rows, records, contain 0 claims. And then the next 4.7% of the rows contain 1 claim, etc., etc. Okay, and then in terms of the exposure, so it does range between 0 and 2. But we can see from the distribution that it mostly is between 0 and 1, with the mode being 1 being the mode, but then the median and the average is around 0.5. And yeah, we can go through each of the variables, and we can see each of the variables whether they're categorical or whether they are numerical. So area is categorical, the vehicle power is numerical, And yeah, I won't go through each, but it's useful to actually understand your data. We then go into data prep. So in data prep, we have to choose the features that we're going to use as variables, predictive variables. We also have to choose our weight, which is our exposure, as well as a response variable or target, which is the number of claims. And yeah, then we also need to split our data set between the training data set and the test or validation set. So in this case, it is an 80%, 20% split. I will be using my test data set as a validation data set. Ideally, it should be split into three because your validation data set does influence, in terms of the parameters when fitting the model. Because it trains the model on the training data, it looks at the validation loss, and then determines what is the best model with respect to the validation loss. Okay, so then we continue with modeling. Okay, so we start with the null model, and the null model is simply the weighted average, right, of the response, weighted average of number of claims, which is weighted by the exposure, and that it's a simple, prediction. That's our null model. It's kind of like a homogeneous prediction for all the records. Okay, then first up, we build a GLM. Now, there are many GLM packages in Python, such as Gloom. Gloom is quite a nice package for fast fitting of GLMs. There's PyGLM, there's PyGLMNet, there's the stats model, there's also the H2O package. Here in this tutorial, I'll be using the H2O package. I think the H2O Python package is quite good. So we start off by initializing a local server instance. This generally takes under 30 seconds to spin up, and once that server is started, we can then essentially start working in the H2O server. So we start by first converting our pandas data frame into an H2O data frame, and essentially then set all our vectors to be categorical, including the numerical. So it's a very simple data set that I'm feeding into the GLM. I'm not doing any hectic pre-processing. I'm basically assuming that the data that we saw is sufficiently prepared for the GLM. So in this case, I'm not fitting any numerical, so they will all be categorical. So we continue. We also set as the offset the log of the weights, the log of exposure. So that's just to make sure that we fix the bias. So we fit a person with a log link function there. And remember, the reason why it's a person family distribution is because we are modeling count of claims. And person is typically the family distribution that we're choosing. Sometimes if there's over dispersion, so where the variance is not equal to the mean, then one can use something like a negative binomial distribution. But in this case, we'll just stick with the person. We do set the lambda, which is the regularization strength, to 0. So that means that there isn't any penalties that is imposed in this GLM. Okay, so we then just train the model. We feed in the offset column, the training data, the validation data, features, as well as the target. And this will fit a GLM model. This takes about 16 seconds using the H2O package. And there's some results that it does print out. I won't go over them because we will do evaluation right at the end. Okay, so then we use the final model and predict the values, and we store those values as in a column named GLM prediction. So this will be used later on when we do a performance, when we do some evaluation, performance evaluation of the models, but we'll also be using this as an initial value into the combined actuarial neural net. So yeah, that's the predicted values. Okay, next up is the elastic net model. So just as I said before, it is a regularized GLM that combines the Lasso and the Ridge penalties. And yeah, we just use the same data as above. And the only difference is that we remove the lambda parameter. We could set the lambda parameter directly to basically determine the strength of the regularization, but we leave it out because, you know, the H2O package would essentially find the optimal value for that lambda parameter through its own internal heuristics. Okay, so then we fit the elastic net model, and this is quick, 0.9 seconds. I believe because here much of the time was done in terms of converting the data into an H2O, converting pandas data frame into an H2O, so it's not really a comparable time, but yeah, so it takes just under a second to fit an elastic net model. Okay, so we carry on. Again, you know, there's predicted values. We store it as part of the elastic net prediction column. We then fit a GAN model, a generalized additive model, which basically allows for fitting smooth functions such as cubic regression splines or thin plate splines, and fitting smooth functions are better suited to numeric variables that are typically nonlinear and that has a very high cardinality. So in this data set, we see the numeric variables vehicle age, driver age, bonus malus, and density. Although I think density is the only variable that has very high cardinalities, about 1,000, just over 1,600 unique values, whereas the others might potentially have less than 100. So it's not really ideal unless one, you know, plays around with the parameters. But I do get a feeling that as I am fitting all the numeric variables, as you know, in terms of fitting smooth functions on those numeric variables, I might, you know, underfit the data. But anyways, it's just to show that one can also fit a GAN model here. Okay, so the H2O package allows you to specify what type of smooth function. So in this case, all the variables with the exception of bonus malus will be fitting a thin plate spline, whereas the bonus malus is a cubic regression spline. And these are the number of knots, and it's basically 10 for each with the exception of bonus malus, which uses 4. Okay, so we fit our model, and this takes 13 seconds to fit. And these are the outputs. Okay, then we predict the values from the GAN model. Okay, then finally we are here at the neural network model. So I'm using PyTorch to build a neural net. There are a number of packages that one can use. There's TensorFlow. You can use the Keras API on top of TensorFlow. But in this tutorial, I'm using PyTorch, and I'm using the Lightning as the API on top of PyTorch, simply because it helps to organize the code. Okay, so how we are going to do this is we're first going to initialize our data class, right? Our data module, which essentially takes as inputs the pandas data frame that we have. And really the idea is to take the pandas data frame, do some pre-processing, and convert it into a tensor. which is then suitable for our PyTorch neural network models. Okay, so we instantiate or we define the initialization function, which copies the pandas data frame and copies all the such as the list in terms of the features, the target, the weight, the batch size, as well as the prior prediction. So prior prediction is necessary for our combined actuarial neural net. And then we have a pre-processing function. So when this data model is initialized, it will do all of this. So copy the data into the class as well, and pre-process, right, the data. So pre-processing essentially includes identifying what are those columns that are objects, so that are non-numeric, and what are those columns that are numeric. And all of those columns that are numeric would go through a standard scaler. And a standard scaler is simply the value minus the mean divided by the sample variance. And then the categorical variables would essentially go through a one-hot encoder transformation. And yeah, so then that's the pre-processing. This will spit out kind of like a number of columns. So for example, if we have a variable, let's just say area, there are 9 levels in area. The one-hot encoding would essentially create 9 columns, and if it's area A, it will indicate root 1. If it's not area A, then it's 0, etc., etc. So there's definitely more columns. So we essentially extract the names of those columns, so that essentially we pass those through to the tensor. Okay. So finally we define our train data loader as well as our validation data loader, and in the data loader we specify what dataset we are using. So the train data loader, we specify the train dataset to be used. There's a batch size, and then there's shuffling. So what this essentially means is that what the data loader will do is you have your dataset and it will shuffle the rows, so it will be random. It will then take the first number of rows that matches the batch size, and it will pass that through the model and calculate the loss, and it will do a back propagation to update the weights, and then the next batch is chosen, etc., up until the full epoch is complete. And there are other parameters that one can use. So there's number of workers, which is 12. Persistent workers is true, pin memory true, and then drop last for the train data loader. And then for the validation loader, so we don't shuffle. We don't want to shuffle because we want that to be consistent when we're calculating the losses. And that is essentially the data module. Now, once we're done with the data model, we can now build our neural net model. Now, in the neural net model, we define our deviance loss function. So in this case, it's the Poisson deviance loss, and this is the equation for the deviance loss function. So this is basically equivalent to the maximum likelihood estimator in the GLM case, where one fits a Poisson log-link model to the data. And we also define our activation function, the exponential activation function. So PyTorch doesn't come with a standard exponential activation function, so we just have to define it, but it's very simple. Okay, once we have that, then we've got what we need to build the actual model. So in this case, it's a sequence of 1, 2, 3, 4 layers, right? The first layer is the input layer here, which is the size of the input dimension of our data set. And this is the number of neurons in this layer. So it's basically the same number of neurons as the input dimension, and then I'm applying a ReLU activation function, and I'm also applying a dropout with a 20% at a 20% rate. So this is essentially good just to make sure that there's some regularization in the model. I'm not overfitting because it's just so many parameters. So it's basically 4 layers. The final layer has 1 neuron. So if you watch my first video, I basically explained that essentially, so if we were to let's just say comment the first 3. So if we were to have just this as our neural network, right, with the Poisson deviance loss function, then this is equivalent to a GLM. Like this is equivalent to a GLM. But we have many layers because we want deep learning. And it really doesn't have to be like this. You can basically, include however number of rows that you want to include. You can essentially, specify how many number of neurons that you want in each layer. Sometimes it's really an art to build a neural network. Or you can even have, other types of neural network architectures like a ResNet. As long as the final layer kind of looks like this, for fitting a combined actuarial neural net. But in this case, we'll just be simple. Okay, so here I essentially manually set the weights of the final layer to be 0. The reason for this is when I'm fitting my combined actuarial neural net, I really want the GLM prediction to be the initial value, and then those weights, so that it's at an optimal loss, right, in terms of what the GLM could have fit. But then the neural net will then start off from that position and find a lower loss. Okay, then we set our loss function, and then this is the forward function, which is essentially taking the neural net and then multiplying it by p. So p could either be the exposure, or it could be the prior prediction, right, where the prior prediction is also taking into account the exposure. Okay, so this here is essentially if the prior prediction exists, right? So you specify that the prior prediction is a GLM prediction and you have a column with all of those predictions, then this is essentially a combined actuarial neural net. But if you don't specify it, this will essentially become a weight values, and this is a simple feed-forward neural net. Okay, then we define our training step, which is essentially, forward function to come up with a prediction, pass it through the loss function, and then log that loss value. And we do the same thing for the validation steps. Okay, from an optimizer perspective, there are many optimizers that you can use. There's the stochastic gradient descent optimizer, there's the RMS prop optimizer, there's the ADAM. In this case, I'm just using the N-ADAM with the default parameters. And then we finally define our train model. Now that we have our data module and we have our neural net model, we then define how the training should be, right? So the training is basically a function of the pandas data frame with the features, weights, target, as well as whether there's a prior prediction or not. Also specifying the number of max number of epochs, as well as the batch size. So we initialize our data module, then we extract our input dimension from the data module. So this is after pre-processing the new columns. Then it will take the number of all the columns. That would be the input dimension, and thereafter we can then initialize our neural network. Then we specify the early stopping, which looks at the validation loss epoch, and it basically waits for five epochs, and if it can't get a lower validation loss within the minimum delta, it will then stop the training, right? And then that is basically then your best fitted model. Okay, then we define our trainer by feeding it the max epochs, and then there's the GPU as our accelerator. I mean, if you don't have a GPU, this can be a CPU, otherwise just simply set auto and then it will figure out for you. Okay, then essentially we fit our model. So in this case, I'm not specifying a prior prediction, and so it will fit a basic feed-forward neural net, and using a GPU. This took about 3 minutes 20 seconds to fit. Okay, but that is the model. We then have to set our model after training. We have to set our model to evaluation mode, and essentially then predict the values based on the input variables. Okay, then finally we get to our CANN, our Combined Actuarial Neural Net. It is the same as the neural net, except this time we specify prior prediction. In this case, it is the GLM. I mean, it doesn't have to be a GLM. It could be the elastic net that we fit. It could be the GAM model that we fit, but we'll just simply use the GLM model predict values. Okay, in this case, the model fit was complete, model training was complete after 1 minute and 47 seconds. So much quicker than 3 minutes and 20 seconds. And the reason here is that it's starting off at a more optimal position relative to just random weights, right? Because GLM prediction is the initial value, so it's starting from that point. So it's very close to an optimal position. Okay, so then evaluation mode, and we use the model to predict the values. And now it's time to evaluate our model. So in this case, it's going to be, we're going to use the deviance Gini. So deviance is essentially the deviance residual. So and Gini is the measure of differentiation, right? So what I mean is that the model, if the model has a very high Gini, it's able to differentiate the lower risk from your higher risk, right? So where lower risk in this case are those with a lower claim frequency, and high risk are those with a high claim frequency. So if it's able to differentiate the low from the highs, the highs from the lows, it will have a high Gini coefficient. Otherwise, it will just have a low Gini coefficient. Okay, so this is my function here to essentially calculate the Gini coefficient. And then I'm using the Poisson deviance function from the model diagnostic package. So model diagnostic package is also another great package to perform some diagnostics on your models. And we will be using this quite a lot. I think it has nice functions to essentially, perform diagnostics quite quickly. So in this case, I'm using the Poisson deviance from that. Otherwise, I can define my own function to calculate the deviance, Poisson deviance. All right, so here is our results for each of the models. So we begin with our null prediction. So the Poisson deviance is about 0.3285, and this is kind of like where we need to start. So if there's any model that can perform better than the null prediction, we should expect to see a lower deviance, Poisson deviance. So the GLM, that is the case, it's about 0.3088. The elastic net performs slightly better than the GLM, and then the GAM model predicts much worse than the GLM model, but definitely better than the null. And this may be due to the underfitting, in terms of the smooth functions that I mentioned. And then the neural network, so this is the basic neural network, it does perform better. It performs better than the GLM. And then our combined actuarial neural net performs even better than all the models, including the basic neural network model. So I think that's a good result. And then if we look at our average response or total response in terms of the actual versus predicted, we do expect the null model to be on point. We do expect the GLM to be on point. The elastic net is on point. The GAM model is on point. However, our neural network seems to have a bias. It seems, to, in terms of the total responses, the total number of claims that it's predicting from our test data set, seems to be understated. So yeah, that's quite of a disappointment. I suppose in this example, it might not be true for other cases. But yeah, in this example, there is a slight bias. Even though we do get a better Poisson deviance, it does have a slight bias in terms of the overall response. Okay, and then from a Gini coefficient perspective, the true Gini coefficient, so if your model is like 100% perfect, you'd get a Gini coefficient of 0.95. So if you remember, when we went through the data analysis, we saw that about 95% of our records have 0 claims. This is kind of similar to that. Okay, then Gini coefficient of our null prediction, 0.18. This is quite low. It's bad. We expect this to be bad because it's not differentiating between high and low risk. It's just an homogeneous prediction. And then our GLM sitting at 0.318. Our elastic net performs better than our GLM. Our GAM prediction is much worse. Then our neural net actually performs quite good, so slightly above the elastic net. And then our combined actuarial network is just doing great here at a 0.35. So yeah, our combined actuarial neural net is performing very well in terms of the Poisson deviance as well as the Gini coefficient. But yeah, there's obviously some bias in the model, and one can essentially play around with the neural net to find the best model structure that can essentially fix this bias. In this case, I won't do that. I will just move on. But in terms of the actuarial process, in terms of getting the best model, one would always have to iterate through the models to then find the best model. Okay, one of the cool things that you can get from the model diagnostics package is a reliability plot. And yeah, a reliability plot essentially is saying if you have, let's just say you bin your predictions, right? And then within that bin, get your average prediction. And you also get your average of your actuals, right? So in this case, average of your number of claims as well as the prediction. So they should be similar. If they are similar for all the bins, then your model is reliable, right? And one way of visually seeing that is essentially plotting, your prediction in your x-axis, and then your estimated actuals, right, in your y-axis. So I'm just gonna zoom around here. So this is where most of our data sits, just around the 10% claim frequency side. So we see here in the very, very low claim frequency, very low predictions, right? We do see an under prediction. Yeah, this is an under prediction, just below around the 5% mark, which then crosses over to an over prediction. Yeah, so it's more or less reliable, but this may indicate that there are some over dispersion in the data. It may. One would have to test for over dispersion. But yeah, it's not truly reliable. It is somewhat reliable, but perhaps we can find a better parameterization of the model. Okay, so another cool feature from the model diagnostics is the bias plots. So remember, I do expect our neural networks in the combined neural network to perform poorly from a bias perspective. And yeah, these are the results here. So all our models is roughly around 0, which indicates that they have no bias, with the exception of our neural network models, which does have a bias. Okay, and another feature is essentially doing the same thing, right? A bias plot by feature. And this basically will help you understand where is it that the model could potentially overpredict or underpredict. So for example, the null prediction, we do expect it to perform poorly by feature because we're not differentiating, and we do expect some features or some other models to perform quite well. So ideally, if your model is performing very well, then your biases should be at a 0 for all the levels. Okay, so I'm not going to go through each of them. Okay, then the other cool feature from the model diagnostics package is the marginal or partial dependency plots. Yeah, so here I'm using Plotly. So I'm using model diagnostics to basically calculate those marginal values, and using Plotly to plot those. So this is the marginal plot for the area feature. So let me just zoom in. So this is the exposure, the sum of exposure for each of the levels of area, and this is our mean observations, right? So observation mean, this is the actual. So if we fit the null prediction, you can see it's kind of like stable. It's flat at around 10%. That's because there are no marginal. There's no partial. It's not differentiating anything. So we do expect that to be quite flat. And yeah, and if we fit, for example, the CANN prediction marginals, so you can see it is quite. It does follow the trend. It will have a slight bias, as mentioned before, and if we fit the GLM does fit through it much better, but that's because there's no bias. So if one corrects with a bias, it should look better. Okay, so I mean, you can go through all of the features. So one example we can go through here is age. So let's just zoom into age here. So you can see GAN. Just try zoom in here with GAN. So you can see GAN here, where it tends to underpredict for the low driver age, and then overpredict for the next range, and then underpredict. This here is a sign that it is, underfitting. And you can see that the GLM actually performs much better because it does follow the mean observation, and then similar to our CANN model. Okay, and yeah, that's it. And I hope this was helpful and useful for you. And yeah, I think good luck now building combined actuarial neural nets, and until next time.